Well, g'day floodies and globe defenders, it's Critical Think from Down Under. So, JTolan Media1 once again finds himself in the embarrassing position of having proved the globe. So here's his criteria where he made a measurement, and for a flat earth, theta 1 equals theta 2 equals theta 3, and the criteria for a globe, that's curved earth, theta 1 is greater than theta 2 is greater than theta 3. And guess what? When he makes the measurements with a proper piece of equipment, a theodolite, he gets theta 1 greater than theta 2 greater than theta 3. So he, by his own criteria, he proves the globe. So what's he going to do now? He's going, uh-oh, I've proved the globe. How am I going to weasel my way out of it? How am I going to come up with the right excuse to get out of this pickle? So here's what he's come up with this time. Oh, it must be refraction. And to go onto the refraction topic, you should go and watch Ruhif's latest video on this, a good video explaining how no, it can't be the kind of refraction that JTolan Media requires. But anyway, let's just play along and humour JTolan Media for a while here. So he's going on, oh, well, it must be refraction. And ladies and gentlemen, what you're about to see here is the greatest data fudging exercise I've seen in a long time. So let's go through it. So he's discovered, maybe by accident, that he could fiddle these numbers to make this curve look like what he wants it to look like. Now, just remember, he has to make refraction fit his measurements, so that he can explain his measurements by refraction. So he's used Snell's law here to graph something. Now, what is actually graphed is a delta, which shows that as you approach the 90 degrees, which is 90 degrees to the normal, which is a horizontal viewing angle, as you approach the angle, the delta gets bigger and bigger. And so, this must be it. If we adjust our viewing angle so that we get close to the normal, that must increase the refraction. Actually, in actual truth, the viewing angle has very little to do with the refraction in the atmosphere. The light will curve according to the refractive index that changes because of the density of the air, and it will curve at many viewing angles, but there may be a very, very loose relationship, but this delta here is pretty much unrelated. And also here he's used N1 and N2. I think he's got them backwards, but that doesn't matter. With only 1, 2, 3, 4 noughts and 2, he's comparing these numbers, which are you're never going to get that comparison of numbers over. He's measuring now a pole that's 100 feet high, roughly. You're never going to get that much variation in the refractive index. So it's a load of bollocks, but it would appear convincing to any flat earther that doesn't know how mathematics and refraction works. So flat earthers, he's pulling the wool over your eyes. He's taking you for a ride on this. Now, this is the pole that I think he's measuring, but it doesn't really matter which pole it is in this case. But judging by the data that he's provided, I've sort of come to the conclusion that this is the pole. And on one of his particular measurements, he can only see the top of that pole because there's a bit of a hill in the way. And this particular measurement is number 4. and he's decided to discard this measurement, which is okay, maybe that's not so great. You just can't do that unless you've got a very good reason. In his case, his reason is not very good. He says that the gravity of the hill there is bending the light, so therefore he can't count that. I think I really do think this deserves a bit of laughter. So it may be true that hot air near the surface of that hill there may bend it a little bit, but also this is a very sensitive measurement, this one. The pole is not very far away. It's only a very short distance. So any small variations or errors in measurement will kick these points one way or another very easily. It's very sensitive to error, this measurement is, because it's such a small distance. But anyway, he's decided that he needs the curve to look like this, so he's fudged the numbers by leaving out that particular data point. Now he's done another bit of jiggery pokery like he normally does, and he's drawn his globe pole height as this green line down there, while at the same time acknowledging that he left out the drop and it really should be closer to the dotted line, but it doesn't matter. He's on the diagram, the visual representation is a deception that makes people think that the globe pole height prediction is down there. And he's also done a bit of jiggery pokery with the numbers here, and he's taken deltas. Now you just can't do that. You have to measure the absolute angles, not the deltas. So actually, I have no idea what he's trying to do. I'm looking at these formulas and that, and I tried to figure it out, but I decided I'll just do it properly myself. And the other thing is, with this diagram here to the right, he's overcomplicating things ever so much. He's saying, oh, it's too hard to do the globe thing properly. Well, look at the diagram. It's overly complex, just trying to confuse the issue. And I'll show you in a little while how to do it properly. So here's his original plot, which formed the basis of his hypothesis that refraction must be possible for the apparent height of the pole becoming less and less as you get further away. So there's a couple of things I've already pointed out about that. And one more thing that I haven't pointed out is he never actually got his measurement angle down close to 90 degrees. This is the measurement range, and you can see that in his measurement range the change isn't so dramatic, even though, like I said, the delta measurement isn't really all that relevant. But you can see that even in his measurement range, all of a sudden we've got a flattening of the curve there already. Now, and as I've mentioned before, he's discarded one of his points. Now, you might think that that's okay, but it actually makes the world of difference because there's so few points. The errors in measurements will make these points be a little bit all over the place, so we need all the points we can get. And of course, his reason for discarding that point is absolute bollocks. Now then, I've plotted in the globe prediction, and this is no refraction, and the flat earth prediction, you see, would be a flat line, no refraction. Now already you can see that the globe prediction seems to be fitting this curve a lot better than the flat. The apparent pole height gets less as you get further away, and this is as would be predicted on a globe. And calculating this on a globe is not so difficult. If you just forget about all that other jiggery pokery that he was doing, you can see that it's just, this is the angle he measured, theta, the angle to the top of the pole, and then all you got to do is account for this drop here, and it's not so hard to calculate. I don't know what he's going on about. So I've modelled this up, and I know this looks a bit complicated, but based on Ruhif's work on refraction, I stole some of the things. Well, not exactly stole, but Ruhif used them, and I had a look, and there's a couple of websites. So where's that one? So this website, refractiveindex.info, they give you a way to calculate representative values of the refractive index of air, and there's a Python script at the bottom that you can download. I downloaded it, and I created a couple of representative refractive indexes, one at the aqueduct and one further up about 160 feet in the air, and I interpolated between them, but we'll get more into that in a minute. The other thing that I would have used, there's an air pressure at altitude calculator, Omni calculator, which I use to estimate what the air pressure might be to feed into the refraction calculation. So back to this, I've got these refraction calculations, so I've used those websites. So at elevation 2953, the atmospheric pressure is roughly that. Temperature I've taken as 25 degrees C, which seems to be around about the temperature when he's doing his measurements. And that gives you a refractive index of 1.0002413. Now I've used this as dry air, CO2 450 parts per million, and this wavelength of light. And then I've calculated, I've gone 50 meters in the air, which is about 160 feet, 3116.90963. Pressure, temperature just dropped by 0.2 of a degree, and that gives a slightly lower index of refraction, 1.0002401. And I've used these numbers, and I've written a bit of code to a refraction simulator, which I've taken some code from Mick West's refraction simulator. So I've just targeted simply to work out my pole height, and instead of using the full refraction equation, I've just interpolated between these 2 points. Now to explain the purple, this is the insane refraction that's required for JTolan Media to meet his requirement. In the green area is the refraction comes out at -4 degrees centigrade per kilometre. That's the lapse rate. The lapse rate required for this purple band here, -196 degrees centigrade per kilometre. Now, if you go to see Ruhus' video, he goes into this at he explains this very well, and in that video he also explains that around a -33 degrees lapse rate, you should get sort of like level refraction, not up, not down. And I've run the numbers through my scenario here, and it works out that at -33 there's hardly any refraction at all, and it needs to be a -196 for it to get an upward refraction required by the flat Earth. So I've also done some estimations on refraction based on JTolan Media's just index of refraction comparison type of method. It just assumes one refraction basically, and the simulator runs through an iteration of many miniature refractions. So this is the graph here of the measurements. I've extended it by 1 point closer to the pole just to have the predictions look a little bit better. I've come up with the height of the pole as 99.2. JTolan Media1 made it 99.1. Not that it makes a huge difference, but I think 99.2 fits a lot better as I do these curves. So the first curves there is no refraction. So then we have to add in some estimated refraction. So standard refraction for the globe, which is a 1.11 R refraction, and an approximate refraction for the flat Earth based on just comparing refractive indexes. And so this light blue line here is, as you would expect, standard refraction lifts it a little bit, but it's still looking fantastic for the measured results. And standard refraction for a flat Earth would cause the pole to actually, apparent height to actually get higher. So there. Now, the flat earthers still need the line to come down here, and we'll work our way towards that. So we've got some more calculations. So using my simulation, I'll show you the code for the simulator. It's pretty boring stuff, but so I converted it to Visual Basic to run in Excel. So I've just taken parts of the Mick West refraction simulation, and I've converted the code to VBA, as I said, and I've just targeted to 1 point. That's the top of the pole. I've tried to find the ray of light that traced to the top of the pole, and then worked backwards from that what the height of the pole would look like. So that's the refraction simulator that I've built into this, and that's this brown line here for the flat Earth, and this green line here for the globe. So far, so good. Now then, we have to answer the question: how much would the refraction have to be to bring the refraction, first of all, in the opposite direction to what it normally is, and then to match what we need it to match to fit this data, which I've said is impossible. And you can watch Rua's video if you want more information, but to change by 196 degrees centigrade in 50 meters is impossible, and that's just not the conditions that JTolan Media1 was experiencing on that day. But when you do the science and plug the numbers in, and we know that flat earthers hate the numbers, when you plug the numbers in, this is what you get. So we'll look at the data, that how it comes out on the graph. So I've done two curves. This one here is the approximation, the one down there, just the single. Let's just do a single refraction based on some refractive index numbers, a bit like that graph that JTolan Media had done. So you can see that's a little bit off. And then this purple line here, it matches the globe fairly closely. So these are the numbers that you would require for the flat Earth to fit this observation. And these numbers are in fact impossible. So just using the standard atmospheric conditions, the globe fits quite nicely to these observations. Now, you'll see why had to translate that into pole height to get any meaningful graph out of this, and you'll see why when I just plot this. Just the elevation angles. I've plotted a representative sample. They're all so close together you can't really make anything out from that. And that's why it's translated back into an apparent pole height, which can give some meaning out of this graph. But anyway, I did all the work. Again, the flat Earth is impossible, and the globe fits quite nicely. Thank you.